Assalamu alaikum and welcome to lecture number 17. In this lecture we are going to discuss about the contribution of single pole or zero factor. uh, in fact, we will continue the topic we started in the previous lecture. We'll also talk about the relationship between magnitude and phase, and we also talk about the all pass systems. So we ended the previous lecture on this slide where we are using the vector diagrams, which are also very helpful. So let's continue. We have talked about the frequency response, and then we talk about the phase response on this slide. So let's discuss something more about it. So you understand we can make the each pole and zero factor can be represented by a vector in the z plane, and you know that the starting point for the pole vector or the zero vector is the position of the pole or the zero. That is where it originates, and it is directed to the uh, point on the unit circle. So as we discussed in the previous lecture, the magnitude response is given by this equation for the particular problem we are continuing. Okay, so that is simply it's equal to the magnitude of v3, which is represented here. So v3 is basically v2 minus v1 minus v2. Okay, so this is where it is represented. Now we change r, right? So that is r can have value of 0.5, 0.7, 0.9 and 1, and we keep the theta. You understand this one is theta, so we keep it constant at pi radians. So if we observe the frequency response, right? So on the, you understand, on the x-axis we have frequency, and on the y-axis we have the response expressed in dB. So you can see that as the frequency increases, the response is decreasing for all the cases or all the values of r mentioned here. The moment it reaches the pi, we have a sharp decrease in the response. So in particular, you understand that for r equals to 1 is represented by the solid line, and you can see when omega equals to pi, the magnitude in dB approaches minus infinity for the case of r equals to 1, whereas although for all values of r there is a dip in the response, but specifically if you carefully notice, for the r equals to 1 we have the response reaching minus infinity. Okay. Similarly, if we talk about the phase response, which is plotted here, so you can see around the omega, right? Again, I will say you understand that it is on the x-axis we have frequency because we are in the frequency domain. So when the frequency reaches pi, because the angle or the theta of the zero is fixed at pi, so when the frequency reaches pi, in that case phase has positive slope in this region. So again, for different values, you understand. So when r equals to 1, the slope becomes infinite. So this slope function is discontinuous. This phase function is discontinuous with a jump of pi radians at this particular location. You understand that we are talking about when omega equals to theta, where we have theta equals to pi. So when omega equals to pi, we have a discontinuity. Now again, when frequency moves away from the pi, you understand we have a negative slope. So let's come to the third graph, which is about the group delay. So since the group delay is negative of the slope of the phase, the group delay is negative around omega equals to theta, that is here, and it dips sharply as r approaches 1, becoming an impulse. Whereas when we move away from the omega equals to theta, that is this region, the group delay becomes positive and relatively it's becoming flat. So I hope this gives you basic idea. Let's consider another example where we have a second order system with a system function or transfer function given as this. To find the magnitude response in dB, we replace z by e power j omega. So replacing this by e power j omega will result into 1 minus r e j theta, e power minus j omega into 1 minus r e power minus j theta, e power minus j omega. So this system has poles at z equal to rj, e power j theta, and conjugate locations at r e power minus j theta. Similarly, this system function has two zeros at z equal to 0. And plot for the pole 0 are shown here. So here are two zeros at the origin, and we have pole here r e power minus j theta, and another pole here at r e power j theta. So expressing the resulting magnitude squared equals to, I hope this you understand, or let me just do it for this one, and I think for the second case you understand how we get it. So let's denote it by hz1. So it is and this one by hz2, so we can write it hz1. So we replace z by e power j omega, so it will be 1 over 1 minus r e j power r e j theta minus e power j times e power minus j omega. So because they are multiplied, bases are same, so the powers will be added, so we can write it as 1 minus r e power minus j omega minus theta, and expressing it into real and imaginary parts, that is in the rectangular format. So it will result into 1 minus r, and this becomes minus j omega minus theta, so it will be cos of omega minus theta and minus j sine of omega minus theta. Okay, so multiplying it by minus r, it will result into 1 minus r, and this will become minus r cos of omega minus theta minus this minus and this minus will become plus, so plus j r sine of omega minus theta. Okay, now taking the square magnitude for this one, so square magnitude of this one will be equal to h1 of e j omega, right, and expressing it into dB, so it will be 10. Okay, so okay, so expressing into dB will be 10 into log of this, so this will be equal to, because the numerator has a value of 1, so log of 1 will be 0, and it will be it is divided, so it will become in it will be something like 0, okay, for the numerator, minus 10 log of, you understand why we take the minus sign, 10, and then the magnitude of this one. So because magnitude of this one will be equal to real square plus imaginary square, so real square will be 1 minus r cos omega minus theta square, plus the imaginary square will be r into sine of omega minus theta square. So if I write it here, I hope that's straightforward. So it will be 1, okay, squaring this, or let me write it. Okay, so I'm just taking the magnitude for this one first. So to take the magnitude of this one, that will be real square plus imaginary square. So real square is 1 minus r cos omega minus theta whole square, plus the imaginary square will be r into sine omega minus theta whole square. So it will result into 1 minus 2 r cos omega minus theta. Okay, I hope you understand the simple formula, a minus b whole square, it will result into a square minus 2ab plus b square. So b square will be r square cos square omega minus theta. Okay, again this one, r square sine square omega, sorry, that's omega minus theta, not theta minus omega, right? So it will be something like, so it will be 1 minus 2r cos of omega minus theta, right, plus r square cos square omega minus theta plus r square sine of omega minus theta. Okay, so that's about the magnitude. So you see, we can take r square common from here. So if I take r square common from here, I am left with this thing. Okay, so you understand, cos square plus sine square result into 1. So that means for the magnitude I am left with, okay, straight away I write here and I say okay, plus and this is r square. So this is the magnitude. Okay, now we are taking the dB. So in dB the products will be we are taking basically dB is basically log base, so taking the log of two things that are multiplied, it will be equal to the summation. So thus we get uh, log. Okay, and the negative sign, you understand why we get negative sign, because when you take log, so for example log of 1 over, for example, a plus b, so the log of the numerator will be 0, so it will be equal to log of a plus b. So this is something, because log for numerator is 0, so it will be 0 minus log of denominator. So this is denominator, that's why we get negative sign here, and also because we are expressing it in dB, so we multiply it by 10, so it will be 10 log of, I hope you understand why we get the negative sign. So for this one we get 1 plus r square. Okay, so 1 plus r square minus 2r cos of omega minus theta. Okay, similarly for the second term we get this thing. Okay, so I hope that's straightforward. So that's how we can find the uh, magnitude response in dB for the this case. Okay, so again for the argument or the phase response, so phase of this will be equal to because it consists of numerator and denominator. So numerator has phase of 0, so we have, you understand, for the complex numbers that it consists of numerator and denominator, then the overall phase equals to phase of the numerator minus phase of the denominator. But here in this case, because the phase consists of only real terms, so tan inverse of real upon real will be equal to 0. So we have 0 minus the phase of the denominator, so it consists of two terms, so we will have arc tangent, right, for the this term, and again minus the phase of this second term. So that's how we find the phase for this one. Again, group delay is just the minus derivative of the phase with respect to frequency. So this is what we get for the group delay. This is the expression. Okay, similarly for the case that we represent the magnitude response in the so this is in the vector diagram notation. Okay, so we have so v3 represents the 0 vector. Okay, and for the pole vector, this is the point of the pole. So and this is point on the z plane. So connecting this with this will give us the pole vector, whereas we have another pole here, so connecting this with this will result into another pole. So in the pole vector case, the magnitude will be equal to the magnitude of the uh, uh, 0 vector, and because we have two poles, two different poles, v1 and v2, so divided by v1 vector, magnitude of v1 vector into magnitude of the v2 vector. So I hope that's clear, right? Because to find the pole vector or the 0 vector, you find the pole or the 0, and then you connect the point of the pole or 0 with the point on the z plane. Okay, so because if we look at this one, we have two zeros at origin, so connecting this right up here, it will give us the 0 vector. Okay, so both the zeros vector will have magnitude equal to v3. Okay, and similarly for the case of the poles, we have one pole here, Okay, so connecting this pole to the point on to this point will give us the uh, pole vector 1, and connecting this second pole to this point will give us the second pole vector. So the overall magnitude response in terms of vectors, it will be equal to, because we have two zero vectors, so zero vector square, because they are same, they are at origin, right? So because they are touching the unit circle, so their length or magnitude will be equal to 1. So that means we can write v3 absolute square, and because its value is 1, so 1 square is 1, so we get this thing. And similarly for the case of the polar vectors, we have two polar vectors, v1 and v2, so we write it here. So on this slide we have a graph for the example we have considered on the previous slide, which consists of two poles and two zeros. And for the magnitude response or the frequency response for this system, that is complex conjugate pair of poles, so making r equals to 0.9 and theta equals to pi by 4, we have this plot. So if we carefully observe this plot for the frequency response, we find that so when the value of the omega roughly equals to theta, the length of the vector v1 becomes small, right? Because v1 equals to ej omega minus r ej theta, and changes significantly as omega varies about the theta, whereas the length of the vector v2, which is pole e power, and which is equal to e power j omega minus r j e theta, changes only slightly as omega varies around omega equals to theta. Thus the pole at angle theta dominates the frequency response around omega equals to theta, as is evident, okay? By symmetry, the pole at the angle minus theta dominates the frequency response around omega equals to minus theta, right? I hope this gives you idea. Anyway, for the case of the phase, if we look at the second figure, the phase angle changes linearly, right? If you observe this region, so if the frequency increases from less than pi by 2 towards 3 pi by 2, so you can see there is a linear phase, linear increase in the phase. Similarly, for the case of the uh, group delay, we see we have maximum delay, that is around 9 samples, and again we have the peak when the between roughly we can say 3 pi by 2 to 2 pi. So to summarize, you understand we have considered two examples, one for the zero and one for the pole. Although in the pole case we had a pair of poles. Okay, but if you compare the two examples, you can see that the contribution for the zeros are opposite to what they are for the poles. So hence the contribution of a pole would be negative of the curves for the zeros, and vice versa. Depending on the value of r, the closer r is to 1, the more peak will be contribution to the magnitude right? And this is based on the previous two examples we have done. For a stable and causal system, there will be no poles outside the unit circle, that you understand that we have done so many times. So I want you to go to the example 7 and example 8, so that you get more understanding and you get clearer concept. You understand in this uh, course we have the reference book or the in fact textbook, that is the discrete time signal processing by L&V Oppenheim. So these are the two examples. I want you to go through it. The next topic we are going to discuss is the relationship between the magnitude and phase. That means by knowing phase, can we tell what will be the magnitude of this system, or by knowing the magnitude, can we tell the phase of phase of the system? In general, knowledge about the magnitude doesn't provide any information about the phase, and similarly knowledge about the phase doesn't provide any information about the magnitude. But for the system described by the linear constant coefficient difference equation, that is, we are talking about the rational system function. You understand rational system function is the one in which the numerator and denominator both consist of the polynomials, right? You understand what is polynomial, right? So if the magnitude response and the number of poles and zeros are known, then there are only finite number of choices for the phase response. Also, if the phase response and the number of pole zeros are known, then within a scaling factor there are only finite number of choices for the magnitude response. So under the minimum phase constraint, the magnitude response specifies the phase uniquely, whereas the phase response specifies the magnitude to within a scaling factor. To explore the possible choices of the system function given the square of the magnitude of the system frequency response, we consider right. So that's the square magnitude, okay. And I think from previous discussion you understand that it can be written as product of the h of ej omega and h conjugate, right? So if we write it in terms of the system function, so we replace z by ej omega, so that means h of ej omega will be equal to h of z, and similarly h steric ej omega equals to h steric 1 over z steric. Steric indicates the conjugate. So for a rational system function, I think you are clear with this equation. H of z equals to b naught over a naught, and product k running from 1. These are the zero factors, and these are the pole factors, and this is in the factored form h of z, our system function. So that means h steric 1 over z will be equal to b naught, k running from b naught over a naught, and k running from 1 up to m, the product, okay. And then again we have ck, so we have ck, and for z inverse we replace, because this is h of z, okay. So we have this. I hope that's straightforward, right? Going from h of z into h steric 1 over z. So we have square of magnitude of the frequency response evaluated on the unit circle. Thus we can write it as express c of z, h ej omega square equals to c of z, and this is equal to h of z, h steric 1 over z steric. So by putting the values of the h of z and h steric 1 over z, we get this equation. I hope that's again straightforward, because we are just multiplying them. So this term, we believe that it's we assume that this one is real, so conjugate of this will result into the same. So that means multiplication of this with this will result into b naught over a naught whole square, and a product of this and this. So we straight away write product k running from 1 up to n, 1 minus ck z inverse times 1 minus ck static z, and similarly for the denominator case. Thus when we are given h e j omega magnitude square, then by replacing ej omega by z, we can construct c of z as we did in the previous on the previous slide. So what information can we get from cz given give us about the h of z? So for each pole dk of h of z, there is a pole of ck at dk, and dk steric minus 1. Okay, similarly for each 0 ck, there is a 0 of ck at ck and ck steric power minus 1, right? So the poles and zeros of ck occur in conjugate reciprocal pairs with one element of each pair associated with the h of z, and one element of each pair associated with h sterics 1 over z steric. If one element of each pair is inside the unit circle, then the other will be outside the unit circle, because they are reciprocal. Another conjugate. Another alternative is that both the elements lie on the unit circle in the same location. So if h of z is assumed to be causal and stable, then all poles must lie inside the unit circle, right? You understand? Because for a stable LTI system function, all the poles must lie inside the unit circle. Now, poles of h of z can be identified from poles of c of z, right? And with this constraint alone, zeros of h of z cannot be uniquely identified from the zeros of c of z. As we have discussed, that causality and stability can help in finding the poles in h of z, but we cannot find the locations of the zeros. So let's consider an example where we have two different stable systems with system function as shown here. h1 of z consists of this one, and h2 of z has values these. So let's find c1 of z. So c1 of z will be equal to h1 of z steric h1 1 over z steric. Okay, so that means we can find c1 of z. So c1 of z will have value something like this, and similarly we can find the c2 of z, and it has values this one. So let's first see the poles and zeros of these two different systems. So if we look at the first one, so it has a 0 at z equals to 1. So it has a 0 at 1, and it has another 0 at minus 0.5, which is represented here. Similarly, they have the pole location which are same, so it has pole at this location and this one. Similarly, for the second case, it has a 0 at 1, which is here, and again it has a second 0 which is at minus 2. So if we just look at the two figures, we just find that although the two responses are identical, the only difference they have is one has 0 at minus 0.5, and the other has 1 0 at minus 2, except these all the poles and the second 0 they have the same location. So finding C1 of Z is this one. I hope you can straight away find H1 of Z, and you replace H1 of the conjugate of this with 1 of Z in the 1 over Z in this equation. So you can get easily H1 steric 1 over Z steric. Similarly, for the second case, you can find easily here. So if we compare the two system functions, that is C1 of Z equals to this one and C2 of Z equals to this one. So if you compare term by term, so you can see we have one, they both have the same poles at the same locations. But if we see the whether C1 and C2 are equal, so we compare, we have 1 minus Z inverse here, 1 minus Z inverse here, then we have 1 minus Z, and again we have 1 minus Z here. So the only different terms are we have 2 and 2 scaling, 2 2s are 4, and 1 plus 0.5 Z inverse and 1 plus 0.5 Z. Okay, so if we simplify them, so you can easily find that this equals to basically this one. So that means the C1 of Z is exactly equal to C2 of Z. So the only difference is the location of the 0. So if we look at this term, because 2 is multiplied here, so we can write it 2 plus Z inverse, and for this case we have 1 plus 2 Z inverse. But in case of the frequency response, 1 plus 2 Z inverse and 2 plus Z inverse, they have the same frequency response. So they have the same frequency response or the equal frequency response, but the phase functions for these two frequency responses are quite different. So I hope this gives you idea that we can find the locations of the pole exactly, but we cannot find the locations of the zeros exactly. Knowing some constant, we can just tell the choices that we have. The phase response can have this option. So I want you to go to by yourself and do the example 10, where you have to determine h of z from cz. So I hope it will further clarify your concepts. So that's all for this topic. Let's start the next one. The next topic is the all-pass systems. So in case of all-pass system, we have magnitude response that is independent of the frequency. So whatever frequency it has, it will have a constant response. So let's consider we have a system that has frequency response that has system response equal to Z inverse A steric 1 over 1 minus A Z inverse. So replacing Z by e power j omega, we have e power minus j omega minus A steric. You understand steric means the conjugate. And we have 1 over A e power minus j omega. Now taking e power minus j omega common, we have 1 here, and steric e power j omega over 1 minus A e power j omega. You understand the magnitude of the complex exponential with unit amplitude is 1, so it has unity magnitude. Now if we take the magnitude of this one, so we have numerator and denominator which are complex conjugate of each other, and hence they will have the same magnitude. So that means it will have 1, and also this one has magnitude equal to 1. So the all-pass system will have a magnitude response that is equal to 1 or constant. So the most general form of the system function for all-pass system is as defined here. HAP represents the all-pass system in Z, right? So that we have summation k running from MR Z inverse minus dk over 1 minus dk Z inverse and k running from 1 up to MC Z inverse minus ek static Z inverse minus minus ek over 1 minus ek Z inverse 1 minus ek static Z inverse. Here is a positive constant. dk's are the real poles, ek's are the complex poles. So for causal and stable all path system, you understand for stability we have the condition that poles must lie inside the unit circle or they have value less than 1, and similarly ek have value less than 1. It may be noted that we have pole for each pole is paired with a conjugate reciprocal 0. So for example, we have a pole here at minus 3 by 4, so we have its reciprocal 0 at minus 4 by 3. Similarly, we have a pole at 1 by 2, so we have its reciprocal at 2, and so on. Phase function for the first order APS is defined as angle of this. You understand that's the system function. So the argument or angle of this is equal to numerator angle minus the denominator angle. So numerator angle equals to minus omega. So we have minus omega minus 2 tangent inverse of real part, imaginary part over the real part. Similarly, for the phase function of the second order all path system with poles located at z equals to r e j theta, and because we have the conjugate poles, right, conjugate complex conjugate pair, so we have one pole at r e j theta, so the second is at r e j minus j theta, so it can be written as argument of this. So you understand that's the expression for the second order system. So it is equal to minus 2 omega minus 2 tangent inverse of this, right, this one, and then we have minus 2 tangent inverse of this one. So with this we end the lecture for today. So see you in the live session. Allah Hafiz.